Chapter 16, Lesson 4. In this lesson, essentially we'll do two calculation problems involving equilibrium and also involving acids and bases. So we had seen an icebox style problem in the previous lesson. Here we'll see another one, and this one will require the use of X. This is a double diamond, a much more difficult calculation. So here's the problem. We want to calculate the pH of a 0.30 molar solution of acetic acid, and the acetic acid formula is given to us and its Ka is given to us. These Ka values can actually be found in reference books. These are in the back of our book, so you can actually look up acetic acid and its dissociation constant. Because these constants stay the same, they are listed in reference books and they can be used and referenced. So by having the Ka of an acid and knowing what kind of concentrations you're beginning with, you can actually predict the pH of the system, which is extremely important. And to do this, we're going to have to set up the icebox. So let's go ahead and do that. Now let's first write out our acetic acid equation. In this case, acetic acid is H3O2. Now there's two ways of doing this. You can either show this as reacting with water, or you can show it directly as dissociating into your conjugate base C2H3O2 minus and H plus. This is kind of a shorter way of doing it, so in this problem I will actually show it like so. The Ka is also given to us for the system, and the Ka, we can put it down here. Your Ka for the system is 1.8 times 10 to the negative fourth, or negative fifth actually in this case. We'll have to use this value. So let's go ahead and set up the icebox. The reason we know this is an icebox problem is because we were asked for the pH, and the pH is a measure of the equilibrium concentration of H+. It's a measure of how much H+ we have in the system. So to get the pH, we'll have to get this value here. The original concentration is given to us as 0.30 molar, so we'll put that in here, 0.30. Our initials on the product side we'll assume to be 0, as we've done in the previous chapters. And then, because we're not given any equilibrium concentrations, we'll have to use X's. So we have to lose from the reactant side and gain on the product side. So we'll have minus X and plus X and plus X. And then for equilibrium, we have X here, we have X here, and we have 0.30 minus X. And now it's a matter of solving for X. So we'll have to plug these values into our Ka. Our Ka is 1.8 times 10 to the negative fifth equals X squared, products, over reactants. In this case, a reactant is 0.30 minus X. Now, in order to help this out, what we'll have to do, we can't really square root. We cannot get rid of the X squared. If you leave the problem as it is and try to solve for X, you'll require the use of the quadratic. So for this problem, you'd have to use the quadratic formula. However, there's a little shortcut that is very often employed, and I'll actually use this shortcut here. I'll teach you it here, but you can avoid using the quadratic. And this shortcut is going to sound strange, and it's going to look a bit strange and even illegal, but what I'm proposing to do is we're going to take this minus X portion and ignore it. We're going to get rid of it. The reason we can do this is because X is going to come out to be a very tiny number. We know this. We know X is going to be a tiny number because your Ka is a tiny number, which means your amount of products at equilibrium is very, very small. In fact, it's going to be so small that compared to the 0.30, it's going to be negligible. So we can actually ignore the X, and this will help us solve the problem a little faster. Now, you can only do this, so we'll go ahead and put a rule down. You can only ignore X if your Ka is different from the initial concentration, from, in this case, 0.30, by 3 orders of magnitude or more. Now what this means is that 3 orders of magnitude means that if you take a look at the Ka is to the -5th, your 0.30 is really to the -1st, so you got 10 to the -1st versus 10 to the -5th. The difference here is 10 to the -4th. So this is 4 orders of magnitude. So we're justified in ignoring x. And we'll show you more of these examples. For the most part, for most of the time for these acid-base problems, you'll be justified in ignoring x. And this will help you solve these problems. In fact, you'll take a look here how quickly we can solve this problem having ignored x. Let's go back and finish up the problem. So again, we have 1.8 times 10 to the -5th equals x squared, now simply over 0.30. So all we have to do is move the 0.30 that way and then square root. So we got 0.30 times 1.8 times 10 to the -5th equals x squared. So x will be equal to the square root of 0.30 times 1.8 times 10 to the -5th. So go ahead and find x in this case. And we find x to be, go ahead and plug this into your calculator. Hopefully you found x to be 0.00232 molar. This is your x. Now, because the x that we figured out was actually your H plus concentration, the problem, recall, asked for the pH. And pH, recall, is negative log of your H plus. So all that's left to do is take the negative log of this value, 0.00232, and we'll get the pH of the system, which in this case is 2.63, and we are finished with the problem. So the pH of a solution of acetic acid that is 0.30 is 2.63. So notice what you can do if you have your Ka of the acid and you know what kind of concentration you're beginning with, you can predict the pH. You can predict really how much H plus you have at equilibrium. So this is applying the equilibrium icebox to an acid-base type problem. So we've done one with the acid. Now let's go ahead and do one with the base. Before we do one with the base, we're going to talk quickly about something called polyprotic acids. It turns out many acids have more than one ionizable hydrogen. What this means is that acids can dissociate more than once. So if you take a look at something like sulfuric acid has 2 hydrogens that can come off. Phosphoric acid has 3 hydrogens that can come off. Now, usually the first hydrogen comes off the easiest, and therefore the first Ka, what we call Ka1, will be the highest. The second Ka will be lower, and the third Ka will still be lower. So the first, technically, hydrogen comes off the easiest. You can think of it that way. Now, for our purposes, the pH will generally depend only on the first ionization. So we'll only consider the first Ka. And the rule here, again, is the 10 to the third, or 3 orders of magnitude rule. As long as the two differ, here, if you take a look at this is -3, and this is -8, these differ definitely by more than 2 orders of magnitude, so we are more than justified to ignore Ka2 and essentially base our entire dissociation on simply Ka1. This is for polyprotic acids, of which there are many. Okay, and then let's go on to weak bases. So the Kb, the dissociation constant for bases, will be defined essentially in the same way as it was for acids. When a base reacts with water, you form the conjugate acid and some hydroxide ion. If you plug this into your K, you'll get your 2 aqueous solutions on top and your original base solution on the bottom, concentration on the bottom. Again, water is a liquid, so we do not put it into the equilibrium expression. And now, having these Kb values for many, many bases, we are able to find the OH at equilibrium, and through it we can find the pH. So essentially what we just did for acids, we're going to do for a weak base. So let's get on it. And these Kb values can actually be used and can be found, rather, in reference books. And there is one in the back of our book. So weak bases, like weak acids, the weaker the base, the lower its Kb. So here you have a very small Kb. The smallest of these three is 3.3 10 to the -7 hypochlorite ion. And so we have ourselves, this would be the weakest of the three bases. The strongest would be your carbonate ion. This would be the strongest, even though it's quite weak on its own. And that is, again, based on the value of the Kb. Remember, because K, just as in Kaa or any other equilibrium constant, is always products over reactants. So the higher the value, the more products you have, the more you have dissociated at equilibrium, is the idea. Okay, so why don't we try this example problem, very similar to the previous one that we did with acids. And the question is, what is the pH of a 0.15 molar solution of NH3? Now, in order to solve this, we'll need the Kb of NH3. Kb values can be found in the back of our book. I believe it's in Appendix C, and we'll show you this in class. But if you look up Kb, you'll find that Kb is 1.8 times 10 to the -5th. And so we can now use this value, 1.8 times 10 to the -5th, set up the icebox, and find the pH of our solution. Again, we're throwing a molarity down for a weak base and asking for its pH. We can predict the pH before actually running the experiment. So let's go ahead and set this up. Now our ammonia, our weak base, is NH3. Let's go ahead and write out the equation for how this reacts with water, setting up an equilibrium system. Because ammonia is a base, it'll accept a hydrogen from water and become NH4+. After water gives up the H+, OH- will be left over. And again, the Kb for this system was given as 1.8 times 10 to the -5th. Or we determined it to be 1.8 times 10 to the -5th. We'll have to use this value to solve the icebox. So the icebox is set up. Go ahead and set up the icebox. As we did previously, water is a liquid, so water will actually not go into the equilibrium expression. We can ignore it. We begin with a concentration of NH3, and that was given to us as 0.15 molar. We'll assume that these are zeros, and we don't have the equilibrium concentrations. In fact, we have to find the pH. So pH will come from here indirectly. In fact, the pH will come from pOH. Well, since this is a base, we'll first get the pOH, and then from pOH we'll be able to get the pH, is the idea. So we'll have to use X's. We must lose on the reactant side and gain on the product side. And because all of these are 1:1 to 1 mole ratios, we simply have -X plus X and plus X. At equilibrium, we have 2 X's, and we have 0.15 minus X. Let's go ahead and set up our Kb equaling our equilibrium concentrations. So Kb, which is 1.8 times 10 to the -5th, is equal to X squared over 0.15 minus X. So we come up against a very similar situation we just saw in the previous problem. And remember, the way we said to avoid the quadratic is we can ignore this minus X. Let's go ahead and ignore it here as well, because the difference between 0.15 and your Kb is more than 3 orders of magnitude, and we are justified in ignoring minus X. In fact, if you were to include the minus X and solve the quadratic, you would find that the answer is the same, considering two significant figures. if you carry out the calculation to more decimal places, it'll differ, but for our purposes, because we are limited by the significant figures, it will not matter. So really, we got ourselves 0.15 times 1.8 times 10 to the negative fifth equals x squared. So let's go ahead and square root both sides, and that gets rid of our squared, and see what you get for x. Go ahead and do this in your calculator. And we get ourselves 0.00164 molar for x. Now remember, x is actually referring to the concentration of our base. So in order to get the pH, we'll first have to get the pOH, since x shows us how much base concentration we have. So to get the pOH, we'll negative log our OH minus concentration. In this case, we've got negative log of 0.00164, which gives us, go ahead and plug this into your calculator, 2.78. Now this is the pOH, so to get the pH, recall we'll have to subtract from 14. So pH will be 14 minus 2.78, which gives us 11.22. And this is the final answer. This is the pH of our system. Notice it's above 7, it's basic, as is consistent with the fact that we have a base. We're actually putting a base into our system. So notice we've done the same thing as we did previously using the icebox. We first solved for x, and then we found the negative log of that number, subtracted from 14 because we have a base. And we'll practice plenty more of these types of problems as we go along. This, I would say, is the central concept of being able to calculate the concentration of a weak acid or base. So this concludes for us lesson 4 of chapter 16.